Emostel.
Hello, you're welcome to this video. In this tutorial, we just want to talk about two more instances that has to do with converting non-linear graphs into linear graph and making important deductions from them. All right, so these two conditions or two cases specified here, okay, is different from the type that we've been dealing with before now. This one involves it's a completely different scenario, and then that is the reason why we need to just analyze them separately, okay, unlike how the other ones are being analyzed. And then also the steps in which the steps we take in solving or in converting this one is a little bit different from the step we took we've been taking in previous conversions. Okay, all right, so let's write. It's quite easy though. In case one, we have a situation where P is equal to KQ. Okay, no physical term is described in this case. No, we're not talking about mass or period or anything. Okay, we're just like, okay, that what are we going to do if we find ourselves in this situation where a physical term, okay, P, is equal to KQ raised power n, where this n is constant and then also K is constant. So which means the two variables we have is P and Q. All right. So no particular physical term is described here, but we are just like having an assumption of this kind of situation whereby we have we have something like P is equal to KQ raised power n, where K and N are constants, then P and Q are variables. So definitely this one is the dependent variable, while this one, this is the independent variable, while this is the dependent variable. So how do we convert a case like this into a linear equation? Obviously, because the independent variable is carrying a power, definitely we are going to get a nonlinear graph. But how do we convert it? How do we get rid of this power and convert the equation to something that is linear? All right, so to go about that, what you do here is to take the logarithm of both sides. So if you take the logarithm of both sides, so you're going to be having something like log P is equal to log KQ raised power n. Okay? All right, and then in the law of logarithm, we have it that law of logarithm says that log AB, like logarithm of two stuff multiplying each other, is equal to what? Log A plus log B. So if we apply that into this, we have log P is equal to log, so we do that, that's log K plus log Q raised to power n. Okay, so that's what we are going to have. And then as we have it that way, you see that there's another law in logarithm which says that log A raised to power x is equal to what? X log A, which means that the power is going to serve as a coefficient to the logarithm of that base. Okay, this is another law of logarithm. So which means if you add something like this, maybe you want to find the value of log log 50 raised power 2, just an example. So the answer is you are going to have it as what? Log 50. Okay, so just making you know that. All right, so that law applies here. So we are going to be having log P is equal to log K plus n log Q. All right, so successfully, we have been able to get rid of that n, which is the power that disqualifies this equation from being a linear equation. I told you in video 2 that the moment the independent variable carries a power, okay, the moment the independent variable carries a power, the graph is not going to be a straight line graph if you plot a graph of the dependent variable against the independent variable. All right, so that is it. But so which means since the power is the thing, is the factor that is causing the problem, or that makes the equation to become non-linear, then we are going to find a way of getting rid of that power. And that is what we just did. We got rid of the power by applying the rules of logarithm. All right, so then as you have it here, if you can check it properly, knowing fully well that k is a constant, so log k2 will be a constant, knowing fully well that n is a constant, okay, and then so if you look into this, okay, p is the dependent variable, while this is the independent variable. So it's looking like something like this. Something is now looking like y is equal to c plus mx. If you compare, okay, this one is like log p, so which means log p is the y, which is we are plotting a graph. Actually, we'll be plotting a graph of log p against log q in this kind of instance, for us to be able to have a straight line graph, a straight line, okay? Then it shows that y is equal to log p. This log q is now like our x. It's now like our x, okay? Then this slope is the n that is beside it here. So, okay, why this c is everything here, okay? So, which means anytime you just have a bunch of constant values, like a bunch of constant values, constants, all the constants comes to form the intercept. But whenever you have a constant that is attached to a variable, any constant attached to a variable is regarded as what? As the slope. Why that variable, the independent variable, okay, is why the other stuff, whatever is it, that this one is attached to, the variable that it's attached to becomes like the x, okay? So that's how you determine it. If you take a look at the equation, check out for the variables involved. Check out for the variable that carries a constant around it. And then also check out for a term that contains entirely constant values. So that term that contains entirely of constant value is always the intercept. But the term that contains a constant value multiplying an independent variable, so that term is the term that contains the mx, okay? Which is, so the constant value that multiplies the independent variable is regarded as the slope, while the independent variable is just like the x that we have. And then this one is just like y, the normal way. So the normal way you would have plotted a graph of y, the normal way you would have actually plot a graph of y against x is the same way you would plot the graph of log p against log q. Because in this scenario, log q is standing as the independent variable, while log p is standing as the dependent variable. While this constant value multiplying log q stands as the slope, and the whole of the thing here, which is also the constant, stands as the intercept. So the rough sketch of the graph is going to be something like, obviously the graph intercepts the y-axis positively on the positive side, and then which is on the log p axis, and then obviously it has a slope m and a positive slope, so which means the graph goes upward because it is a positive slope, it's a positive graph, so the slope is positive, so therefore the graph will go upward. If the slope was negative, the graph will go downward. And this is the positive intercept on the log p axis, which stands for our log, this log k, okay? And then what do we have? Log k, then this n log q, okay? You can find the slope using any 2 points across the graph, and then you are good to go. Find the slope using any 2 points across the graph. So from here to here, okay, it represents the change in log q, and then here to here. represent the change in log P. And so, as usual, we are going to have it that, as usual, you're going to have it like slope, okay, is going to be equal to change in log P divided by the change in log Q, and it's going to be equivalent, to what? To N. It means the N here stands as the slope of the graph, okay? And then the intercept is what? Is log K, and that is that as per that. All right? So at the intercept here, whatever is it, the value is, we know that log P is going to be 0 there, and then you can have it 0 is equals to C plus MX plus log K plus MX, then same to the other side minus log K and all that. So whatever is it that you just try to do depends on what you're looking for, depends on the things that you have. So you use what you have to get what you want. And then in as much as you just know how to find your way around it, you can be able to apply all the deductions to make some important conclusion regarding the stuff, the physical quantities that you are comparing to each other, or the one you the graph of the one you plot against the other, okay, or the dependent variable and the independent variable. So whatever is it that you require, you can easily deduce it from the relationship in as much as you have your way around it. You know your way around it. So that's how it goes, okay? So definitely we are going to solve a couple of questions that will require us to apply all of these things. Then by then, I believe it will make more sense to you. Let's move on to case 2. So moving on to case 2. Case 2 is the Boyle's law. From the statement of Boyle's law, we could deduce that what? The pressure and volume are inversely proportional. That is, the pressure is inversely proportional to the volume. So which means when pressure increases, volume will decrease. So it is practical. It is something you know. If you press a container, okay, the container will reduce in size because you are pressing it. And then the amount of gas contained in the container will reduce. And that is the reason why in the presence of the gas, the excess gas trying to escape, in order to give way to the pressure, the container could burst or could, if it finds an opening, then the gas will escape from the opening. But the amount of gas that will be contained in the container depends on the amount of pressure you apply. So the basic line is just that when pressure increases, the volume will decrease, and when pressure decreases, the volume will increase. So when you relieve the container, then the volume too of that, the gas content in that material will increase because you relieve it, you release the pressure, okay? So that's it. So Boyle's law explains that, and so from that deduction, we have it that pressure and volume are inversely proportional to each other. So if you want to introduce a constant of proportionality, you know, you have to introduce a constant of proportionality before this proportional sign will change to equality. Mathematics, okay? So mathematics says that we can change this proportionality to equality by introducing what? A constant of proportion, okay? So let's say the constant is K, or you can have it as P is equal to K times 1 is K, so you can have it as P equals to KV, or you cross multiply, and then you have K is, or you can say, you can have it as what? PV is equal to what? Is equal to K. So when you say PV is equal to K, what this is just trying to tell us is that the product of pressure and volume is constant. Okay, so the pressure at a particular instance multiplied by the volume of the container at a particular instance is going to be equal to pressure at another instance multiplied by the volume at that other instance. So which means that the value we'll get from the product of pressure and volume at all instances, as far as that specimen is concerned, is going to be constant. That's what it means. Mathematics is trying to speak English. The product of pressure and volume is constant. So which means that P1 V1 is equal to what? P2 V2 equals to P3 V3, and so on and so forth. That's what you have. The product of pressure and volume will be constant. Okay? So that is what happens when we have this kind of relationship. All right. So I don't just want to go into the mathematics of it, start explaining, start telling you while this like this, because it's a ratio thing. But just understand that this thing means that the product of pressure and volume is constant. So therefore, the pressure multiplied by volume at a particular instance will be equal to the pressure at another instance multiplied by the volume at that instance. And you keep having the same value for the product of pressure and volume all through. But that is not really where we are going. So where we are going is that if you plot the graph of pressure, okay, and you plot the graph of pressure against volume, let's say the volume is in cm cube, and then this one is in mmHg or whatever is, or atmosphere, whatever is the unit of pressure that applies to that experiment. Okay, so, and then we have this, mmHg stands for millimeter mercury, is one of the units of pressure. Okay, so if we plot the graph, experiment shows that if you plot a graph of P directly against V, a graph of P against V directly, we are going to have this kind of graph here. We are going to have this kind of graph. A graph that is asymptotic to the two axes. So we have the vertical asymptote, we have the horizontal asymptote. The asymptote is just like trying to tell us like a point that the thing is trying to approach, but it will never get there. So this graph, this line will try as much as possible to touch the volume axis, the V axis, but it will never get there forever and ever. So regardless of the value, as you are increasing the value, as the value is changing, okay, this towards this, the more the value changes, the more the tendency of this line trying to approach it, but the tendency is infinity. It will never be able to approach it. Do you understand it now? So that's how it will keep going, it keep going like that. So this kind of graph cannot really give us anything productive or anything deductive. We cannot really get something out from this kind of graph. So hence, we need to find a way to convert it from a non-linear equation into a linear equation, or look for a way to plot the graph in such a way that it will give us a linear output. So we now discovered that we can get a linear equation, or a linear graph rather, by choosing to plot a graph of P against 1 over V. So this one is now going to be Cm raised to power minus 3, that is per cm cube. Okay, so that's what we are going to have here. This one is mmHg, or atmosphere. Okay, and then this one is in per 1 over V in Cm raised to power minus 3. It's now negative because it's now like the volume is now a denominator. Okay, so that was that. So if you plot the graph of P against this, okay, experiments show that you are going to have a straight line graph that actually passes through the origin, because from the look of the equation, there is no intercept. There is no intercept, because if you look at the equation says P is equal to KV, K over V, or you can say P is equal to K, all right, multiplied by 1 over V. So P being K multiplied by 1 over V, if you look at it very well, so you have it as, if you plot, this K is now a constant, which serves as the slope, okay? The constant of proportionality is now the slope, okay? And then this is the dependent variable, while this one is the independent variable for this graph. So which means you are plotting the graph of P against 1 over V. If you plot the graph of P against V directly, you get this kind of graph, and which you are not going to be able to deduce anything from it. But if you plot a graph of P, if you choose to plot a graph of P against 1 over V, then you're going to have a straight line graph that passes through the origin. And then the slope of the graph, okay, the slope of the graph, that is the change in P to change in 1 over V, is going to give you the value of K, which is the constant of the proportionality. All right, so this one is just like an example of y is equal to mx, okay, where our y is this P, our x is this guy, and then our m, okay, is now the K. All explained in video 2, so you can always refer to that video to understand the instances where the graph passes through the origin. So how you can really identify it, you can identify it because the equation will not have an intercept. So when you do not see anything like a constant standing all alone, okay, you don't see a constant term all alone, it means that that graph is a graph that passes through the origin. And then when you see that the slope is positive, it means the graph goes up. When the slope is negative, it means the graph goes down. And so that is just that as per that. So these two instances are just necessary for us to just refer to, so that you can, whenever you see things similar to that in other physical experiments or anything or any equation, you'll be able to know how to go about it. All right, so if you still don't understand some things, okay, after the explanation, feel free to contact me at any time. I'm going to break it down to you, all right? So because our slogan in Emostel Academy is for you to learn, and then you understand, and then you practice what you understood, and then so that you can aim for what? For excellence, all right? So apply this in your everyday study, and you'll always be great. You come out great, okay? See you in the next video, and bye for now.